Okay, let's try out another problem. So for this one, we're going to talk about something called critical resolved shear stress. What it means is if I have, I don't know, some metal bar and I'm pulling on it, well, I can calculate the stress on that. It's just simply what is the area right here, what is the force right there. That is my stress. Stress is equal to force over area. Now, what is different for us is that we have to remember that this metal bar is actually made up of metal crystals. And those crystals, when they deform, are going to deform most readily along particular planes and in particular directions. So, for example, let's say that this guy is made up of a whole bunch of atoms, which it is. And so I'm going to draw the most perfectly close placked plane. So it's actually at an angle here. Okay, so that is my plane from earlier problems where you had this kind of triangular plane for a face-centered cubic. Maybe this is aluminum we're pulling on, and so that's that plane right there. Now I'm pulling along this, but my normal is over here. That's my normal direction, so it's actually at an angle right there. And so that angle is usually given with a phi. So the second thing you realize is that, yes, while that's the plane now that's going to most easily deform upon, I have to also realize it's only going to deform along certain directions in that plane. So I might have, I don't know, like these are my closest packed directions right here. And so I'll just draw one, trying to make sure they always come down here. I'm going to say that that direction is, we'll go with this way. So now I have a close packed direction right there, and I'm going to say that it says lambda. So my critical resolved shear stress is going to be equal to my stress that I'm actually, that's the yield stress right there. And I'm going to multiply it by, let's see, cosine of phi and cosine of lambda. And so this will tell me the critically resolved shear stress. Because if I have a stress that is large enough, it is going to cause it to shear along these planes. And what happens when it shears? Well, when it shears, that leads to plastic deformation. Okay, so the big thing is it's a really easy equation. You just need to know what the yield stress is. You plug it in here and you can figure out when is it going to shear or not. So what's our problem? So our problem says we have a single crystal, that's always good. So okay, single crystal of aluminum. And it says that the slip plane normal makes an angle of 28.1 degrees with the tensile axis. So here's my tensile axis, I have some sort of tension, and here's my normal direction right here, and that is making an angle of 28.1 degrees. So that's equal to phi. Then it says that there's three possible slip directions. And it's asking us which of those directions are most favored, and also if plastic deformation would begin, when plastic deformation would begin. So let's give those three directions. So our three likely candidates are equal to 62.4 degrees, 72 degrees, and 81.1 degrees. These are the possibilities here. So which of these directions is it most likely going to slip along? Well, slip occurs when this part is a maximum, okay? So we already know one of the angles, we already know phi, so we just need to figure out lambda. And so since it's cosine of lambda, that means the smaller the angle, the more likely it is for it to slip along it. So this guy right here is the smallest angle. That will be the most favored direction for it to go along. If I was to plug in, I could plug it in for all of them and I could see that numerically. Okay, here, I'll go ahead and show you. So cosine of 62.4, well, that's equal to 0.46. Cosine of 72 is equal to 0.31. You can see we're getting smaller. If we go to 90, it would be 0. And then finally, cosine of 81.1, so getting really small, is 0.15. So this is the biggest. It's going to have the largest chance for it to shear along that direction. Okay, So the next question it asks, it says, okay, if, let's see, plastic deformation begins, that's when we finally shear. And this is going to happen at a tensile stress, okay, of 1.95 megapascals. It said, what is my critically resolved shear stress? Well, this is a super easy problem because we already have all the values we need. So all we have to do is just plug into our equation from earlier. So I have 195, oops, sorry, 1.95. There we go, 1.95 times cosine of 28 degrees, that was the first one, that was cosine of phi, times cosine of 62.4. I'll write it as 62.4 even though we already know what the value is. And if I plugged it in, what I get is that this is a value of 0.8 megapascal. So that's my critically resolved shear stress. And we are done. We've got it. So thank you for listening. Hopefully this helps you. I'll see you all next time. Bye-bye.